A Zener diode whose circuit symbol looks like this is used to regulate voltages. It can help to maintain a constant voltage. Say I'm using a Zener of 6 volts, then the voltage stays at 6 volts. It doesn't budge, it doesn't change. Oh, it almost reminds me of a stubborn donkey. And if you're wondering why I said this, you must listen further. Now first of all, let's look at the VI characteristics of a Zener diode, and for that we'll first look at the forward bias and then we'll look at the reverse bias. And the Zener diode actually operates in this reverse bias region. So when you are forward biasing a diode, you're connecting the P side to the positive terminal of the battery and the N side to the negative terminal of the battery. So in this case, the electrons and holes are swept across the junction and a large current flows through it. If I draw this on the VI graph, then I would get something like this. The current increases at a certain voltage which is called the cut-in voltage, which in case of a silicon diode is about 0.7 volts and in case of a germanium diode is about 0.3 volts. Now in case of reverse bias, the current is practically 0 and at a certain voltage which is called the Zener voltage, the current increases sharply. And this is what we are interested in. This is the constant voltage that we talked about a short while ago. The voltage which does not change. See, the current over here in forward bias is in milliamperes, and if I have drawn this also in milliamperes, this practically is 0. Now instead of a milliampere scale, say I use a microampere scale. So the current in case of reverse bias, if I am drawing it in microampere, then I can show a tiny current and then that current increases very sharply at breakdown. So this current is actually in microamperes and this current is due to the minority carriers. Now what do we mean by minority carriers? There is an extremely small concentration of electrons on the P side and holes on the N side. These are thermally generated minority carriers, which means if the temperature is increased, the concentration of these carriers will increase, because in that case you will have more electrons which will move from the valence band to the conduction band. So if an electron jumps from the valence band to the conduction band, you get a hole over here in the valence band. But even if the temperature increases, the current over here still remains in microamperes. If the temperature increases, the current is not going to be in milliamperes. But if you look at the reverse characteristics, you will see that at a certain voltage, an extremely large current is flowing. Now over here we are talking of a reverse saturation current, which means the current is saturated, it cannot increase beyond this value, and then all of a sudden we find that a very large current is flowing. Now let's see that how are charge carriers produced in such large numbers that we have a reverse current which is in milliampere. Maybe it could be say about 200 milliamperes of current which is flowing in the reverse direction. So let us see how is such a large current produced. The first mechanism by which this large current is produced is known as avalanche multiplication. So let's take a look at what happens. These thermally generated charge carriers experience a force due to the applied potential and hence electric field. The barrier voltage at the junction does not prevent the charges from crossing the junction because they are actually moving downhill. Say this is the direction of the potential barrier, because this end would be at a higher potential and this end would be at a lower potential, so the positive charges are moving downhill, and for the electrons, if they are moving uphill, it is actually an accelerating voltage. Now, as the electrons move at high speeds, they collide with the crystal ions and impart sufficient energy to rupture covalent bonds. Now, in addition to the original carrier, we have new electron hole pairs which are created, and these once again start accelerating, colliding with other crystal ions, producing electron hole pairs, and this process is going to continue. The cumulative effect of this phenomena is that we have an extremely large number of charge carriers. It's somewhat like an avalanche of approaching charges, and this is called avalanche multiplication, and the diode in this case is said to be in the region of avalanche breakdown. So you can see that the few minority carriers collided with the crystal ions and in turn produced a very large number of charge carriers, which results in a large current. Now, this was one mechanism by which charges were produced. There is another mechanism by which charges can be produced, and that is called Zener breakdown. In case of Zener breakdown, the field at the junction, the electric field which is present at the junction, might be sufficiently strong to pull electrons directly out of their covalent bonds. So charges are pulled out directly by the strong electric field, and electron hole pairs that are created in this manner help to increase the flow of current and in the reverse direction. Now, this process of charge creation is called Zener breakdown, which means electrons are directly being pulled out by the electric field. There is no collision taking place over here. It is not that you have charges colliding with other crystal ions and leading to electron hole pairs, but the electrons themselves are being pulled out of their covalent bonds. Now, this happens at an extremely high field of about 2 into 10 to the power 7 volt per meter. To achieve this high field, generally the Zener diodes are heavily doped, because if they are heavily doped, the depletion region will be thin and it will be easier to acquire these high fields. But if the diode is not so heavily doped, if it is lightly doped, then a higher voltage, say a Zener diode which is heavily doped has a breakdown voltage of about 6 volts. But if it is lightly doped, then the breakdown voltage will be higher than 6 volts. Now, whatever the mechanism of conduction, whether it is avalanche or it is breakdown, in both cases it is termed as a Zener diode. So now you can see from the graph that the voltage across a Zener diode remains constant even if the current flowing through it varies over a fairly wide range. Now, this is an extremely useful feature, and I am sorry for calling it stubborn as a donkey, because that was just to help you remember that the voltage does not change, it remains the same. In the next lesson, we will discuss how is a Zener used as a voltage regulator. And before we wind up, just a few quick questions. Try these questions to test your understanding. The answers are given a short while later.